Hi, I'm John Merritt, Director of Applications Engineering at Ideal Power. Today, Mike Barron, Senior Firmware Engineer, and myself will be demonstrating the advanced microgrid features of our 30 kilowatt Stabiliti multiport power converter. All of our demos were recorded in Ideal's Research and Development Lab located in Austin, Texas. The 30C3 converter has a 3-wire, 3-phase, 480 volt AC power port and 2 DC power ports, enabling high-efficiency solar and storage microgrids in one compact enclosure, which weighs about 140 pounds. Multiple 30C3s may be paralleled to support larger microgrid applications. Our demo setup utilizes 4 30C3s in 120 kVA nameplate configuration. In this demonstration, we're going to show you the response of the converters to step load changes. We'll step loads down, both in real and reactive power, and we'll step loads back up once again. In doing this, we'll show how the microgrid responds to, again, fairly dramatic changes in the load of a building, simulating lighting coming on and off, other equipment turning on and off, motors, air conditioners, things of that sort. And again, as with our synchronous start, we're looking for stability and shared power as we make these transitions. So we'll start as before with 120 kilowatts of real power, 16 kVAR of reactive power. We'll then step down real power in a 64 kilowatt step, and we'll actually step up kVARs in a 64 kVAR step. So these again are dramatic steps in power change. Mike?
All right. So first thing we'll do is we'll start up the microgrid again. As John mentioned, you can see we're back up at 120 kilowatts to begin with. And the first thing we're going to do is we're going to drop 64 kilowatts of real power. Capture that on the scope for you to see. And as you can see, the voltage and current waveforms are continuous. There's not any particular anomalies or distortion here. The current stepped down. The voltage remained more or less constant. The next thing we're going to do is we're going to add in 64 kVAR of reactive power. Let's get a picture of that. Again, the voltage remains nice and uniform all the way through. The current changes a little bit. As John noted, we now have a phase shift. So it's gone from being very resistive to being very reactive.
And if you look at the monitor, one thing, if you look at this monitor, you can see how, again, the 4 systems responded to those step changes. The signals, as shown, are all well balanced. Each is contributing his fair and quarter share of power to the microgrid.
Okay, now we're going to take the 64 kVAR off again. We're going to capture that on the scope. Here you can see the change in the phase shift again. Before the step load change, we had a big phase shift between the voltage and the current. Here's the step load change, and now they're much more aligned. And then finally, we're going to add back in the 64K of real power, taking us back up to our full load condition. As you can see, the magnitude of the current jumps all the way back up. The voltage remains continuous and uniform. There's no particular abnormalities or distortion there.
And you'll see that entire set of sequences here. Again, it's all about shared loads and shared balance loads between the 4 converters. Each transition represents the step down or step up. So, for example, reactive power here is green. That is when we took it to 80 kVAR. We then subsequently dropped it back down to 15 kVAR. And then back up again. And now the white line is real power, and we're back maximum at 30 kilowatts per converter. Thanks for your time today. We really appreciate you dialing into this microgrid demo. Please contact us if you have any additional questions regarding our products or technology, and have a great day.